How do we simplify square roots when addition and subtraction is involved? Well, first of all, let's start with an example of an addition problem with two square roots which can't be simplified. Alright, so square root of 13, there are no perfect squares in 13, and there are no fractions, and that square root is not in the denominator of a fraction. Right, so these are fully simplified irrational numbers, but we would like to add them together. So in this case, if you're asked to simplify, the problem isn't with each number individually, but the fact that we have a sum means that there's more work to do. So fully simplified in this case would mean to do the addition if it can be done. And we can determine what the sum is using the distributive property. Right? Notice that this is the 2 times the square root of 13, right? And this is 5 times the square root of 13. So we actually have a square root of 13 that's been distributed to a 2 and to a 5. Alright. Now I know 2 plus 5 is 7. Right? And then the commutative property tells me that I can switch the order of these two things and write this as 7 times square root of 13. And we do that just so that if you didn't happen to use parentheses, that it wouldn't be confusing. We wouldn't think that maybe that this is the square root of 13 times 7, right? And it can kind of look like that sometimes if you're not careful with your square root sign, if it kind of tends to go just a little bit too far over the other number. Alright, so we write the number that's not in the square root out front. Okay. Another way of thinking of this is kind of like an algebra problem. You've got 2 of something plus 5 of something, and so altogether you have 7 of that something. Right, and that's similar to if we did maybe like a 2x plus a 5x. You're just counting up how many x's you have altogether. Alright, this one, 6 square root of 11 plus square root of 11. There is a number here being multiplied by the square root of 11, and it's implied that that is a 1. We have one of those square roots of 11. Right, so adding, we have 6 of them plus 1 of them, and altogether we have 7 square roots of 11. Alright, 5 square root of 8 minus 2 square root of 8, that's 3 square root of 8. Now this one's slightly different. In the last two examples we had square roots that couldn't be simplified. We had a 13, we had an 11, but now we have an 8. And an 8 does have a perfect square in it. This is really 3 times the square root of 4 times 2. And 4 is a perfect square. Right, so I'd have the square root of 4 is 2, and then I can't take the square root of 2. Right, numbers which are outside the square root get multiplied, so I would now have 6 square root of 2. Alright, how about this one? The way it's written now, we can't subtract. Remember, if you in algebra, if you had something like 2x minus y, we can't subtract because x and y are not the same thing. Right, so for my radicals, I've got 5 square roots of 18, and then over here I don't have any square roots of 18. It's not the same thing. So to see if this one can be simplified, the only thing that I can check right now is to see if perhaps this square root of 18 could be simplified to the point where it's a square root of 2. Right, so let's try that. I know that 18 is 9 times 2. So I know that this is 5 square root of 9 times square root of 2 minus square root of 2. Right, and that square root of 9 is 3. So I now have 15 square root of 2 minus 1 square root of 2, and that's 14 square root of 2. Alright, now I'm finished because the square root of 2 contains no perfect squares, and I've completed the subtraction problem that was in the original problem. Alright, what do we do if we're dividing sums of irrational numbers? Alright, so right now it's tempting to just do 6 divided by 3, but that would be incorrect, and here's why. This is really, dividing by 3 is really 1/3 times 6 plus square root of 18. Right? So by the distributive property, that 1/3 is being applied to the 6 and the square root of 18. Alright, so if I'm going to do any division or any reducing, I'd have to divide two things here. I'd have to worry about the 6 and also about the square root of 18. Another way that you could think about this is, could I use the distributive property to take anything out of the 6 and the square root of 18, something that could be reduced by the 3 that's below. So if I could take some number out that might cancel with that 3, then that would work. Alright, so let's actually go ahead and see if we can do anything with this problem. Alright, so I have a 6 plus square root of 18. I know that that's 9 times 2. And the square root of 9 is 3. And that leaves me with the square root of 2. Okay? And now it looks like I actually am going to be able to do something with this. And I can tell that because 6, 3, and 3 can all be divided by 3. Alright, so to finish this one off, from the numerator, I can use the distributive property to factor out a 3 from each of those numbers. There's a 3 that was distributed to each of them. Okay, and 6 divided by 3 is 2. And then factoring out a 3, I get a 1. Right? And to check this, notice I could just go backwards. 3 times 2 is 6. 3 times square root of 2 is 3 square root of 2. Right, and that's divided by 3. And now I have 3 over 3. Right? And I can cancel those out. And that is the identity property. Okay, because this is really 3 over 3 times 2 plus square root of 2. And since that 3 over 3 is a 1, I know that this problem is the same as if I didn't have that 1 there at all. Right? So I could rewrite this, and my final answer would be 2 plus the square root of 2. Okay, because I'm just multiplying by 1. Right? How about this one? 5 minus the square root of 12 divided by 4. Right? So both of these terms in the numerator are being divided by the 4. Alright, so I have 5 minus, I'd like to be able to rewrite the 12 as some sort of a perfect square. I know 12 is 6 times 2. I also know that it's 3 times 4, and I like that one because I know that the square root of 4 can be calculated. That's 2. Alright, so I'll pick that one. And that's 5 minus 4 can be square rooted. That's 2. 3 cannot. Okay, and that's all divided by 4. Again, it's kind of tempting to reduce this and say 2 can be divided by 4, but I have one other term to check. This 4 is also dividing the 5, and 5 cannot be divided evenly by 4, so this would be considered fully simplified as it is. Alright, this one, very tempting. We've got a 6, a 12, a 3. Surely there must be some division that we can do. Alright, so let's find out. 6 minus square root of 12, I just did that one. I know that that's 2 times the square root of 3 divided by 3. Alright, so now if I want to reduce this, I need some number that 6, 2, and 3 can all be divided by. And there is no number that works. Right, so even though 6 can be divided by 3, and even though 2 times 3 is 6, and there's some numbers that look similar here, there is nothing that could be distributed out of the numerator that I could cancel out with my 3. Alright, so this is also in lowest terms and fully simplified, and this is my final answer. Okay. 3 plus the square root of 49 over 10. This one's nice. The square root of 49 is a perfect square. I know that that's 7. And I can keep going with this one now. 3 plus 7 is 10. And 10 divided by 10 is 1. Alright, my second one, I have 3 minus the square root of 49. Okay, so square root of 49 is 7. I know that 3 minus 7 is negative 4. And then I can reduce my fraction to negative 2 fifths. Alright, so notice we're simplifying the square root first, then doing the subtraction in the numerator, and then seeing finally if the fraction can be reduced. Alright, and that's it.